In this question number 4, we have this halogenal alkane. So this is a tertiary halogenal alkane. The carbon with the chlorine is bonded to 3 other carbons, tertiary halogenal alkane. And this reacts to sodium hydroxide. And this is a nucleophilic substitution reaction. So nucleophilic substitution means it is a hydrolysis, using aqueous and an OH. So that means in water, hydrolysis. If you use it in ethanol, you're more likely to produce alkene instead of a nucleophilic substitution. It will be a elimination. Show the mechanism. Even though this is an A2 paper 4, they can ask you anything from AS. This mechanism is a tertiary halogenal alkane. So I'm drawing a skeletal. If you want, you can draw a display, I guess. Carbon chlorine. Not really a full display, but a partially display, kind of like a structural formula. So this is delta minus chlorine, delta plus carbon. The first step that will happen, so step 1, you will do heterolytic fission. Heterolytic fission is a term stated in the AS syllabus. This is slow, this is rate determining step, and you will get a tertiary carbocation. Make sure your carbon is bonded to carbon. This is what you call a tertiary carbocation. Intermediate. It's good to label as part of your mechanism, and you will learn, you will get better at it once you start to label some stuff as you go along. After that, from here to here is the second step. This is going to be the fast step, and this is where the hydroxide will just attack the poor electrons, rich attack poor electrons. Then you're just going to get OH like that. So even though I show the hydroxide attacking like from the back, it really doesn't matter. It doesn't really attack from the back because this is carbocation. This carbon is trigonal planar. So what actually happened is you have a trigonal planar plane like this, and it's not actually attacking from the back or anything. There is empty orbital above and below the plane because it's trigonal planar 120 degree carbon sp2 hybridized. So that means your hydroxide from the lone pair of the hydroxide can attack from the top, or the hydroxide can attack from the bottom of the plane with equal chances. Not that your final product is chiral center, is optically active, but in the case where these 3 groups are different, then you can get the potential chirality that will come from carbon being bonded to 4 different groups, and then you will get a racemic mixture as a result of this carbocation intermediate trigonal planar geometry, equal chances of being attacked by the nucleophile from the top and bottom of the plane. You will get a racemic mixture which will not be optically active even though you have a chiral center, but you don't have a chiral center there, so there's not much point talking about that. That's the end of that 3-mark mechanism question. Now we have a graph kind of thing here because this is actually part of a longer question on rate of reaction. You use a large axis of sodium hydroxide. If you use a large axis of sodium hydroxide, we can say the concentration of the sodium hydroxide is roughly constant. And not changing when you use a large axis of it. So what is actually changing then? So only the tertiary halogenal alkane changes. But we don't know. The order of reaction with respect to the tertiary halogenal alkane. So this is why we have a graph of this tertiary halogenal alkane plotted against time. So the initial concentration means at time equal to 0. What is the original concentration? It's not exactly at 0.60. This is 0.58. Am I correct? Yeah, because it's 0.52, 54, 56, 0.58 mole per dm cube there. Usually this kind of question involves drawing a tangent, that is a tangent at t equal to 0 to work out the initial rate at time equal to 0. But we're going to have to read through the question. What do they want? They say it is first order with respect to this tertiary halogenal alkane concentration. What is meant by... Oh, I thought they actually asked for what is meant by first order. So the order of reaction is defined as... Order of reaction is not asked here, but order of reaction is defined as the power to which you must raise the concentration to in the rate equation. So to get first order from the graph, what is meant by half-life? They want half-life. I did talk about it earlier. That they didn't want the order, they want the half-life. So half-life is the time taken for the initial concentration to fall to half its value. Time taken for the initial concentration to fall to half its value. Now calculate the half-life for this reaction. Show all your working. Very typical of this type of question in paper 5 these days, but it could also come out in paper 4 as well. So they want construction lines, so more than one. They want half-life, they don't want initial rate. So 0.58 divided by 2, I get 0.29. So 0.29 is going to be there. So there's my construction lines. And then I use my ruler and then show going downward like that. So my ruler is not perfect, but it's supposed to be somewhere in between there. If you could follow that, it should come exactly in between there. So it's exactly in between 40 and 60. So that is 50. So that is 50 from 0 to 50. So the half-life, the first half-life, because you cannot just do one half-life, you have to get at least 2 half-life in order to show if they are constant for first order reaction. So when you do 0.29 further divided by 2, you're going to get 0.145. So this is 0.15. So this is a bit tricky. Well, not that bad actually on my diagram. So that is where my line comes to. So the second half-life is the time taken for this blue concentration to fall to half its value. So the time taken is from here 50 to 90. This 90, how am I going to read this actually? So if that is 90, then there's 92, 94, 96, 98. So there's 98 seconds. But of course, the second half-life is going to be 98 minus 50 because it's not all the way from 0. It's from this blue color mark here. So 98 minus 50, I get 48 seconds. You will see that within experimental errors, this is not like half the value. This is not like double the value. This is very close to the first half-life. This is called the second half-life, which is 48 seconds. Okay. So I already shown construction lines. So what I do really next is to just, write down some stuff. So the first half-life is that. The second half-life is that. So what can I conclude? My half-life, so more than one, my half-life are constant within experimental error. So therefore, it is first order with respect to these concentrations I'm changing, which is the tertiary halogenal alkanes in these questions. Now next one, what would be the effect? What would be the effect on the half-life if I double my initial concentration of halogenal alkane? Well, what we know about the half-life stated in the syllabus, candidates should be able to state that the half-life for a first order reaction is constant. So what is meant by constant first order reactions? It is governed by this relationship, which is ln2 over the rate constant. Of course, it's stated in the syllabus as 0.69 divided by rate constant. ln2 is just natural logarithm. ln2 is 0.69 something. And this bottom thing is your rate constant, which will remain constant at constant temperature. There are no concentration terms in there. So it doesn't matter what happened to the concentration. A first order reaction will not be affected when the concentration of the halogen alkane changes. The next question, you want to use the graph to determine the rate of reaction at 80 seconds. It's a curve, so you need to draw a tangent at 80 seconds. That's the only way you can get the gradient. Tangent at 80 seconds. So 80 seconds is going to be here. So here it is, 80 seconds. So I'm going to draw a tangent. Let me use a different color. Let me use red color. Is that good? Nope, that is not very good at all. That is not a good tangent at all. So just give me a minute. Let me try, and that is not a good tangent at all. That is not too bad, as you could see. Okay, so that connects. Is that all right? So that looks alright-ish as a line. So gradient at this tangent might not be the most perfect, but you want it to be a tangent kind of like only touching the surface. You could probably get away with this one, like a bit lower, like this, like this, like this, like this, but it wouldn't change that much compared to the poorer version I did earlier. So you get a right angle triangle now. So your change of the x-axis from 0 all the way to, what do you have here? This is going to be 140. 150 is there. So this is 145. Is it 150? Hang on, just give me a minute. So this thing halfway in between. So this is 150. So you have 1, 2, 3, 4, 5. So 142, 144, 146. So there must be 146 second. And what do I have on the y-axis? A lot easier. 0.40, 0.42. So 0.42 minus 0. Your change in y over your change in x. 0.42 minus 0. This is mole per dm cube. And at the bottom, I have 150 minus 0. This is second. So on top, I have mole per dm cube. At the bottom, I have second. So my unit is going to be mole per dm cube divided by second. So I got to show all my working, right? So I'm showing all my working. And just press 0.42 divided by 150 on the calculator. I get 2.8 times 10 to the minus 3. Do not forget to show your units. There's mole per dm cube per second. So just putting in the final answer now. And mole per dm cube divided by second. The next thing we are told that this comes down to this rate equation. So calculate the value and give the unit for the rate constant. Pretty stingy of them to give only 1 mark. But then K equal to, rate divided by the concentration of the tertiary halogenal alkane, which is basically this thing here. So we have the rate, which is 2.8 times 10 to the minus 3. And the unit there is going to be mole per dm cube per second. Do we have the concentrations for these halogenal alkanes? Well, let's have a look at the question earlier. Not really, apart from this initial information, 0.58 mole per dm cube, 0.58 mole per dm cube. Okay, so K there, this is mole per dm cube. So that is the unit of the concentration. Concentration unit 1, concentration unit 1. So 2.8 times 10 to the minus 3 divided by 0.58. I get rate constant of 0.8276 times 10 to the minus 3. That is quite a lot of significant figure, considering that this was only 2 significant figure and this was 2 significant figure. I need to think about what is appropriate number of significant figure, and this is second minus 1. And my final answer is just that, and keep putting in the values there in the space given. That's the end of that 9-mark question on rate of reaction.